So welcome to perhaps the second last session, because next week is a public holiday. So we will have the last session in the week thereafter. So the recording from last week is something which I uploaded recently, and that is mainly about the quantum phase estimation algorithm. And this is relevant for the project. So what I wanted to do today in the beginning now is to say a little bit about the second project and see if this is something which you feel is interesting enough. There are several variants which you can choose. And then I wanted to give you a quick summary of the phase estimation algorithm, because that's a part of the second project, for those of you who want to follow that path. And then I wanted to venture into a discussion of some of the applications of quantum Fourier transforms beyond the quantum phase estimation algorithm. And this is an application or an implementation of the quantum Fourier transform, which requires actually quite some knowledge about numbers and encryptions and so on. So I will try to keep that at a kind of more overarching level, because there are topics there as well which I am not too familiar with encryptions and number theory and so on. So that means that I will essentially just repeat what you will find in textbooks. So the algorithm which is then very relevant for that topic is Shor's algorithm. Now, I've placed it in project number 2 as an option, but I don't recommend it unless you are quite familiar with number theory, because it requires a lot of basic understanding of what's behind the typical encryption algorithms. So I'm coming back a little bit to it. So the things which I will do today is more to give you a broad overview of the topic. And then I leave it very much up to you to decide whether you would like to do that. And I think that in itself is perhaps closer to a good semester work. So it's a more difficult topic. But let me guide you a little bit through the outline of the second project. And please feel free to come with inputs and ideas you would like to follow up. As I said, I mean, you're not locked to do what we suggest. So these are just suggestions. And I know that some of you are interested in exploring different topics. And you should feel free to do that, because as I said, this course is a little bit, how to say, is a little bit more special respect to other courses, in the sense that it was it was tailored as a self-study course, but then we decided to run lectures, and these lectures have been different from year to year because the audience has been different from year to year. So that means that the lectures may actually be made on the go, as you probably have seen with the last topic now, as you will see today. But I wanted to point to you where we have the projects, and so that we can have a small discussion of them. And I was also thinking that for the remaining parts of the semester, so we will typically have 15 weeks of lectures, but then we are going to use these sessions for discussions of the projects till the end of May. So that means that Ruben and Karen will hang around and we can discuss the projects as well. So it doesn't mean that even if we stop lecturing, it doesn't mean that we will not have an ongoing activity here. Okay, so I just wanted to point to you, some of you are familiar with these things and some less. So if you go into the project folder, so one of the things which we did in project 1 is that we were a little bit lax when it came to the format of the project. So some people decided to just answer question by question, but now we would like you to write this more like a scientific report. So that means writing it in terms with an abstract. You would have an introduction to the topic. There will be a general theory discussion. So if you're discussing the quantum phase estimation algorithm, that would be a place where you could put the general theory. And then there will be, in our case, an implementation of the algorithms, and then the typical results and conclusions, etc. The same way as you would frame a normal scientific report. Now, for those of you who are interested, and this is actually, so this serves in a way as a kind of help for many who have perhaps not written a scientific report yet. There is a set of lectures by Anne Rumi. I mean, she's one of the directors of one of the big European journals. And she has actually a series of lectures on how to write a good abstract and a catchy title. So take a look at those notes which you have here. Feel free to look at them. So writing an abstract here is actually a very nice introduction to it. And sometimes we are, how to say, many people actually don't know exactly how to frame the abstract. And the abstract is an art by itself in a certain sense, because this is where you catch the attention of the reader. I don't know if you have some feeds from the preprint server Arxiv. That is a common preprint server where you can find different types of scientific articles. You can find particle physics, quantum physics, computational science, etc., etc. And some of these archives have a daily feed with hundreds of new articles, especially if you're looking at a topic like machine learning and quantum computing. That means that when I scroll through this list every morning, if the abstract isn't catchy and the title isn't catchy, I just jump over it because you don't have the time to go through hundreds of articles every day. So writing a good abstract is actually quite important. So we want to have this element in the second project. So as I said, in the first one, we decided that you can more write it as you wanted. But for the second one, we have a kind of format here where you can take a look at that one. And there are also examples of projects here. So evaluation grading shows you how we actually will grade the second one. So I hope that sounds okay. Take a look at these things. I mean, you have all the material here. Feel free to use it as you want. If we now go to the second project, which we partly discussed in the previous weeks, but I just wanted to bring up some of the alternatives which we have. And there are more possibilities, just keep that in mind. So we have at least 3 different parts. You can actually choose other ones if you want to. So we have one on implementing quantum Fourier transforms, and then the phase estimation algorithm. And what we thought then is that you could use that one to extract eigenvalues of some of the simpler Hamiltonians which we had in project 1, like the 2x2 matrix. Or you can replace that with other types of problems which you may be more interested in. Then there is one, I know there are people who've been studying by themselves, quantum machine learning. There's one which we propose there. There are also people who want to work with quantum Boltzmann machines. So that's an alternative, and it fits people who are following the course called Physics 5429 on machine learning, or Physics 4411. So that's another possibility. And then I know that there are other suggestions from you guys. So feel free just to mention those to us, and we can give you feedback on whether we think that is enough for the second project or not. So we discussed loosely many of these things before, but now I just wanted to guide you through some of these. And one of the variants is basically the one on quantum Fourier transforms. And that is a very important algorithm in quantum computing. And it's, how to say, we could almost say one of the flagships of quantum computing, one of the early ones. And it's actually useful. It can be useful to have it implemented and understand what goes on. So the kind of idea is that you try to rewrite your own or write your own code for basic quantum Fourier transform. And there are some questions about the mathematics, etc., etc. And I'd say that Hunt's book, chapters 6.1 to 6.4, gives you hopefully enough information so you can actually write your own code. So following those sections should have enough information in overall. So we were thinking then of some basic steps where you do this for 1, 2, and 3 qubits. You find the transformation matrix. So you can, as we discussed during the lectures, you can rephrase everything in terms of a matrix, a unitary matrix, which then transforms the original basis into a new one. And you can write that one out analytically. And then you could compare the matrix times a vector multiplication with a quantum Fourier transform you have implemented. So these are the kind of small steps on the way of writing a full algorithm. And then you can generalize it to an arbitrary number of qubits. And then the thing we thought of is actually to implement the phase estimation algorithm for 1 and 2 qubits as an example, and then try to generalize that one to more qubits. And then we thought of looking at, again, this kind of simple Hamiltonian, which you had in project 1, but you can decide whether you want to do that one or whether you're interested in other problems here. So that was that part. Then we have, so this is just basically what we had before. And this is actually the part which I only recommend if you have lots of time, which you probably don't have. And also if you're familiar with some number theory and encryption theory. So, yeah. No, I would say this is a topic which easily can take more time than just the rest of the time, because I put a deadline to the 7th of June. So this is something I would recommend if you are familiar with the topic a little bit and would like to explore and write your own algorithm. So you can still do it. You can take this view, which I will do in the lecture today, where I just give the basic ingredients. In Hunt's textbook, there is actually a pretty detailed description on how you implement it. So this is fully doable, but keep in mind that if you want even to factorize a very small number, you're going to need a lot of qubits. So that's one of the drawbacks. So the actual implementation. So the reason why Shor's algorithm became so popular is that you could show that you could decompose a number in terms of prime numbers, and you could factor it in at much faster, with much less operations than you would do in the standard encryption algorithm, which is called the RSA, which we are coming back to. So you can look at this as an implementation and follow very much many of the steps which you have in Hunt's books or in other texts, and perhaps compare that with the standard implementation of our RNSA. So that's fully doable. But I would say this is something which may require a little bit more time. Yeah.
But if you know the number theory background, if you know that, does it then require that much time?
No. So what I would say then is that if you want to do this, you just take out the other parts and you only focus on implementing Shor's algorithm. Because then, I mean, you will have to use a quantum Fourier transform. So I would say this part itself, this is just one variant of the project. But I would, in order to have the full benefit, I would normally recommend that you have some background in number theory or some interest in it. And that perhaps, I mean, in your research or in the work which you have, encryption and these techniques play an important role. So you've probably seen that my focus has been more on studying quantum mechanical systems. That's the field where I come from. So today also during the lecture, you will see that I will be on a shallow ground, because this is pretty outside my comfort zone of what I normally deal with. So I'm just mainly going to give you the basic overview. Now we have one on machine learning here. So there's one alternative. Oh, this figure's become pretty large here. And this is if you're interested. And finally, we also have an alternative based on Boltzmann machines. I know that some of you are interested in that. So this would be something which would be more self-study piece, and you could collaborate with other people and discuss with us as well on how to implement them. So these are, again, more exploratory projects, whereas what I defined here as both the machine learning project is a pretty straightforward if you're interested, but I recommend that only if you have a background in machine learning. So if you never studied machine learning before, I mean, you shouldn't do that. But just so some of these projects, as you see, since we have this course, which is a more self-study course, I want people to have more options in what they want to study. Any questions so far?
We can also do something completely different.
Yes. So just shoot us an email and tell us what you would like to study.
Yeah,
and then, yeah, she said so.
Thinking about state preparation algorithm.
Yeah. So the thing which is important is that you feel that this is something you can do within the next roughly 2 months or even less than. So we put a deadline to June the 7th. I hope that will be enough. I just pushed the deadline a little bit. But as you've probably seen, we are always flexible with deadlines. I mean, the most important thing is that you find this fun, okay? That's the most important thing. So this is about the projects, those which we have been suggesting. So summarizing, 2G here is a project by itself. And I would recommend that only if you know a little bit about the topic, the background for it. Because else, I mean, it's more, you can implement it if you follow the recipe in Hunt's book. But the deeper understanding follows from the background before that. What is state of the art? What is being used today? If somebody does this, I'm actually even tempted to come up with a small prize, which means probably a book. Okay. So let me then remind you a little bit about some of the things which we discussed last week, or rather, which I have uploaded as a video last week. And I just wanted to say a little bit about, and just remind you quickly about the quantum Fourier or the quantum phase estimation algorithm. So the quantum phase estimation algorithm, so the video should be online, is essentially you looking at a unitary transformation. And a unitary transformation acting on this basis gives you an eigenvalue and the eigenvector, obviously. And the eigenvector for a unitary transformation is given by, you know, that the eigenvectors, when you square it, it's equal to 1. Because when you take U transpose times U, that's equal to the identity matrix, which means that the eigenvalue is equal to the absolute value of 1, which means that you have an arbitrary phase here, which needs to be determined. So this arbitrary phase is an unknown quantity. And that allows you, with the quantum Fourier transform, it allows you actually to determine that phase. And the basic steps of the algorithm is to first implement a quantum Fourier transform, but on qubits in what we call a register. And then when you perform this, first you do a Hadamard transformations on each single qubit in that register. And then you perform a control U operation, which is a controlled rotation. And at the end, when you've done all this, you perform an inverse Fourier transform to extract this angle phi. So I just wanted to remind you of some of these technicalities, which are also in the lectures there. So essentially, what you do when you did the quantum Fourier transform is that you would encode the information of a given state. So if you have 2 qubits, J0 and J1, This would give you 4 states. So the number of states you can produce are 2 to the power of the number of qubits. So which means that you would have for 2 qubits, you would have 0, 0, 0, 1, 1, 0, and 1, 1. And then with 2 qubits, what we did when we did the Fourier transform was actually to encode this either as a binary integer or as a binary float. And we ended up using a binary float because we divided by a binary integer, and then we have this factor of 2 pi before. So we made a compact notation where we would describe a state like this in a binary floating point representation. And you can decide whether you start with J0 or the last qubit, n-1. So this is just a notational convention. So you can always interchange that. So just keep in mind that this way of setting it up has just a minor consequence for the way you order the operations. And in our case, this n would be the number of qubits. So a typical setup for a standard transformation here is that you have a register with a given number of qubits, which you place in the state 0. This is your computational basis. So one of the things which we also discussed 2 weeks ago is that this computational basis is also an eigenbasis of these rotation matrices which we implement. And so then we perform first a Hadamard transformation on all the qubits in this register. This is a state which we want to find the eigenvalue of. And this state here is due to the operations which you have, these rotations, which then act on different qubits. So you can decide whether this one acts on this or that. And that is simply given by the way you're ordering the representation of a given state. So what we found then, some time ago, 2 weeks actually, is that this operation here just affects these qubits. So this is a controlled rotation or controlled U-gate. And then you perform these operations and then you ended up with a new state. So when you perform all these operations, what you would do then is to have an inverse Fourier transform on these states here. And that inverse Fourier transform would give you back the original representation. So the kind of idea is that you the phase you want to find is then defined by the number of qubits you have. And if you have just 1 qubit, so since these take values 0, 1, that means that you can only have a value. If you have only 1 here, you see that all the other ones disappear. So with only 1, what you end up with then is just either, since this is 0, you end up either with 0 or with a 0.5. So that means with only 1 bit, you can represent a floating point, only 2 floating point numbers. If you have 2 bits, you can represent 4 floating point numbers, 0, 1 divided by 4, 1/2, and 3 divided by 4. And then when you increase it, you can represent more and more numbers. But you know that a computer is a finite engine, which means that you can only have a finite number of bits. So unless you have an infinity of qubits, so you could actually have many qubits, it means that from a quantum computing point of view, you can actually perform these operations on a larger set of bits. So the precision of your answer depends on how many bits you use. So this is already one drawback, because if you look at, and what you will appreciate then is actually the variational quantum eigensolver for finding eigenvalues. Because if you look at this one now, this becomes a very long set of operations. And it means that you need to find physical realizations which live long enough for you to be able to perform these operations. And what happens then normally is that you will have so many additional uncertainties with noise, etc., that your computational basis may be spoiled. And then when you have done your operations, you actually don't know exactly in which state you are. So that's a basic problem with this, because you see quickly here, if you have many qubits, you're going to do many operations. And each such controlled U-gate is actually a physical process which you implement on states. So every qubit here could be an electron which is trapped in a small harmonic oscillator-like trap in semiconductors. So you have one electron in each trap, and then you're manipulating one electron at a time with these different gates. And the typical manipulation could be you applying a magnetic field to one specific electron, or you could apply a laser to one specific electron. So the gates, which you actually realize physically, are manipulations of these states with electromagnetic control engines, like a laser, or just you adding a magnetic field. So that means that everything you do here, you see quickly why this is not the way you would implement the solution of a quantum mechanical problem on a quantum computer. But it is an interesting academic exercise, and we can run it. And when you write the report, and if you do this part of the project, then it's easy to actually link that with, how to say, a criticism of this algorithm and compare that with what you did in project one. So that would be a very useful conclusion. So linking these results with what you would have from project one. Any questions so far? So the rest of the slides here contain more technicalities, where we simply look at these different circuits which you can set up. So this will be just one qubit, which means that this number phi here, which you want, this is what you want actually at the end, can only be 0 or 0.5. So that's not so exciting. And this would be the kind of circuit you would realize if you want to do that type of operation. So this is a state which is left unchanged and whose eigenvalue you want. And then you would first perform a Hadamard, and then you would perform a rotation, and then you would perform a new Hadamard if you want to make a measurement. But in general, what you would do here is actually to have an inverse Fourier transform. And if you do that, you will see that the different operations here, and this is something we went through the slides and last week and the week before. So you would have this state, which would simply be the Hadamard and tensor product with the state here. And when you perform the controlled U-gate, which is this one with a rotation, where this is 2 to the power of 0, which just gives you 1, then you simply have this rotation in front of it, and you end up with this state here, because you see that this factor does not affect psi, so you can actually put this inside. So then you have simply the 0 state, and then a rotated 1 state. And that's the new state which you have. And that's a controlled U-gate. And then you can do the same here if you want to make a measurement. So if this is your task, you want to make a measurement and see what state you have for this 1 qubit, then you would simply get either phi 0 equal to 0. If that is 0, then you get the final state is just 0. And if phi 0 is equal to 1, you get 1 here. Then there is a similar example with 2 qubits, and then you would have simply the tensor product of the first qubit. So this is after you've done the Hadamard transformations and done the rotation on that qubit. Then you would simply get this state here. And then you do the next one, and then you get the state psi 2, which is this one. And then you would simply have, then when you do all the operations, you would get a state which is given by 2 rotations on the original state phi, and then multiplied with these tensor products which you have here of these Hadamard rotated states. And there are some small tricks which I'm not going to repeat here, but you can actually, when you do this, you can rewrite these states in terms of these qubit values. So you would have phi 0 equals 0, 1, or phi 1 equals 0 and 1, and then the same here. So you would do this is the same as doing a quantum Fourier transform operation on 2 qubits in this register T. So that is equivalent with that. Then the basic recipe is to apply an inverse Fourier transform, because these are unitary operations. And then when you do that, you can retrieve this value phi. And the project deals with you first implementing a standard Fourier transform, and then implementing the quantum phase estimation algorithm. And if you follow the steps here, at the end in these lectures, you will also find the basic algorithm for setting up the basic steps here. This is a central algorithm because the QPE, or the quantum phase estimation algorithm, enters Shor's algorithm for factorizing numbers. So having coded that one would be a necessary step for implementing Shor's algorithm. Yeah, and here you can see the basic structure. So you would perform Hadamard transformations. You have all these different rotations on each qubits, and you can decide whether you want to do the ordering, whether you start with the first qubit or the last of these qubits in the register is something which you define. And then at the end, you have an inverse Fourier transform. And with that inverse Fourier transform, you compute the final phases. And there's an algorithm here. So I'm just going to skip this one because this is roughly what I recorded for last week. And we are going to go back to the whiteboard. So any questions so far about the tasks for that part of the project and the material which you need? So as I said, Hunt's book in section 6.4 contains the basic elements for writing your own code. You should also try to compare your own code with what Qiskit gives you. And with Qiskit, this is how to say, when you write your own code and you compare that with Qiskit, which is just some few lines, it's sometimes a little bit irritating. But I think it's important to actually write your own code here, because that gives you a feeling of what is going on. I wanted to remind you of these things because they go straight into that specific project. Then on the other hand, if you want to do something else, clearly this is something which is very much up to you. We spent some time on this because the quantum Fourier transform and the quantum phase estimation algorithm play a central role in quantum computing. And it is one of these algorithms which was, how to say, broke the ground for quantum computing, actually. So what we are going to look at now is take a kind of bird's view on Shor's algorithm. And in order to do that, I need to give you first some basic elements from the way encryption is done. So since I'm not fully comfortable where all of you are, maybe for some of you this will be too easy, and for other people it may be totally unknown. So let's see what happens. This is actually the second time I present this stuff, and each time, or the previous time, I just confused myself again. Okay, so let's look at Shor's algorithm here. So it has two parts, and it depends on the quantum phase estimation algorithm. So that is an essential part. So you having a quantum Fourier transform and a quantum phase estimation are actually essential ingredients here. So this was introduced back in '94. And I remember when I was teaching the basic quantum physics course in '99, there was quite some hype around it. And we did some discussions of quantum computing and some basic elements. But then the field lost a little bit momentum, essentially because there were no actual realizations of quantum computers. And then in the last decades, or in the last 10, 15 years, there's been an explosion. And nowadays, there are many companies who build their own quantum computers. So the algorithm has two parts. So one is the classical part. So let's just list them. So this is a kind of entry point to the algorithm. And the classical part is actually based on was grounded in number theory. And this is, I have to confess myself, this is a theory where I have a pretty shallow knowledge, except the kind of basics. And it relies on modulus arithmetics. So I'm just going to remind you quickly about some of the basic elements. And it relies on modulus arithmetics. And a process which is called order finding. And that's an important element. And a process called order finding. So I will come back to these things, but I'm actually going to underline this one and also this one. I will try to give you a kind of basic understanding of what that means and why the quantum variant or the probabilistic variant allows us to be able to actually perform these operations with much less floating point operations. The only problem is that it requires many qubits, and you will be pretty disappointed even for a trivial number like 15 or 21. The number of qubits which are needed for the operations are quite minor. So, but still just showing the feasibility sent shocks through the encryption community. So like when you log into your bank, like you probably have this kind of small thing where you write a code. So the type of encryption which is done, which allows you to log into your bank, hopefully safely, is something which is an essential part for the encryption industry. And then the second part, so classically, it is actually an almost intractable problem. So the above is classically almost intractable. It can be done, but it's almost intractable to decode if you don't have the right information. And but it can be efficiently implemented. If you have a probabilistic quantum algorithm with a quantum algo. So let me quickly remind you of some of the, what we normally call the modulus or modular arithmetic. So you've probably seen this relation here with a number a, which is equal to a number b, and then it's often written like a modulus and n, right? So the modulus is actually nothing but a reminder of the Euclidean division. So if you have a number, suppose you have a 9, and now I'm going to use the notation which you would include if you write a Python code. So this is the Python symbol for modular division. So this, as I said, is a modulus, it's a reminder of the Euclidean division. So if I take the number 9, so this should be a number 9 here, and I take with a, then this is equal to 1. So the modulus, just to quickly remind you, that is the reminder of the Euclidean division. Okay, so if you look at the way you would encode this, an A, B, that is the same as A minus and then you would have the floor. So I'm just writing this as a command here of A divided by B times B. And just to remind you of the floor of X, that is the largest integer, which is greater than X, not greater than X. So if I take, for instance, a number like, so if I do the 5, let me just give you an example. If I take 5 modulus of 7, this is actually equal to 5. Just try it out. I'm just giving you some of these numbers. I hope you don't get offended if I bring up some of these simpler relations here. You also have minus 9 modulus 12. It's actually equal to 15. Because if you do the, if you take floor of minus 9 over 12, that is actually minus 1. So you can quickly see that when you do that, you will get a number which is 15, even if it looks very strange, minus 9 modulus 12. So these are some of these kind of operations which sometimes not all the numbers are intuitive, but these are operations which are then widely used. Now, there is another element which is normally needed. So the modulus division or the modulus operation with modulus arithmetics. So you can have a number x, y, and then modulus with a number z. This is something you would then write out as x modulus z multiplied with y of modulus z. And so you have normal arithmetical operations which you can perform with a modulus operation. Then there is another element which is normally used. So what I'm discussing now is the classical way of encoding this. So this goes back to the first point here, the classical part. And I just wanted to show you some of the basic elements which enter the classical part. And then we are going to move into the way this is implemented with Shor's algorithm. So there's another quantity which we need to define, and that's called the greatest common divisor. So what we need to compute then is to break a number into their prime numbers or their prime factors, and you're often interested in the greatest number. So if you take a number like 21, we know that that one just breaks down into 3 and 7. So the greatest common divisor would be 7 here. Another thing you should just remind yourself about is if you look at a number n, this is an integer. So when I write it n, this is now an integer. This is a number which we can write in terms of prime factors. So we could have a p0 to the power of e0, p1 to the power of e1, p2 to the power of e2, etc., up to a p of n minus 1, and then e of n minus 1. So just to give you another pretty boring example, if you look at a number like 32, this is 4 times 8, but we would have this as 2 to the power of 5. So we would have p0 equal 2 and e0 equal to 5. So finding the greatest common divisor is also something which enters these algorithms. And another example, if you take 99, that is simply 9 times 11, and that would be simply 3 to the power of 2 times 11 to the power of 1. So that's another example where P0 is equal to 3 and P1 is equal to 11. Now, there is a result from number theory which says that the most difficult case is the case where you have only 2 prime numbers to find out how that factors out. So any number can actually be, any such number can be encrypted. And there is a famous algorithm which is called the RSA, which is named after 3 mathematicians, Rivest, Shamir, and Adler. And accordingly, the most difficult case, so this is something which I'm just stating here. The most difficult case is when n has only 2 prime numbers. So this is a result from number theory, and I'm simply just stating the result without any proofs and why it is so. Okay, so the mechanism for finding this is this RSA algorithm, which is one of the standard ones. And the kind of test case is actually a number n, which can now be broken down into 2 prime numbers, p and q. And the problem of factoring a large number into 2 primes is actually equivalent to solving another problem, which we are coming back to after the break, because I see we are a little bit over time now. So after the break, I will say a little bit more about the standard way you would do that, and then we move into Shor's algorithm. Well, let's take a small break, eh? So the problem of factoring n, so this could be a large number. Normally it is a large number. Into these 2 primes, that is actually is equivalent to solving a following problem. And let me just bring this up here. So that is equivalent to solving a problem where we have x to the power of r equal to 1 of modulus of n. And what we have is positive integers. So let me just give you some text as a background here. So we have positive integers, x and n. And x is assumed to be smaller than n with no common factors. And the order of, so this number r is called the order. So the order, and I'm coming back to what this is, the order r is defined, now let me just rewrite it, is defined to be the least positive number or least positive integer r, which solves xr equal 1 and modulus n. So there is one trivial solution to this case, and that is when x is equal to 1 or minus 1. then that has a trivial solution. So let me try to give you what this order actually is. So this order finding problem is defined by the order of some specified x and n. And this order finding is actually believed to be a classical difficult problem. So this order finding, and I will try to baby step you what that means. Order finding is believed to be a classically, if not intractable problem. I should say intractable here, but I'm going to put difficult problem. So let me show you an example which can hopefully illustrate a little bit of this kind of order finding. So suppose you take the number n equal 21, which is then given by 3 times 7. So the way you would proceed with this order finding is that you would try to solve this equation by starting with a random guess. So if you think of 1 times 1, which is equal to 1, obviously, that is the same as 1 of modulus. So let me just keep that one of n. So suppose now that you start with 1 for this number x, and then you have 2 times 2, which is equal to 4, and that is the same as 4 modulus n, and now n is 21, okay? So I'm not rewriting 21 again and again here. Then, if I continue like this, do 3 times 3, so that is 9, and that is the same actually as 9 of n. It doesn't become the same, so 16 is equal to 16 modulus n, but then I have 5 times 5, which is equal to 25. This is actually equal to 5. I think it's, no, it's 4. I think it's 4, yeah. 4 modulus n. And this continues now till we get to 8 times 8, which is 64, and that is equal to 1 of modulus of n. So this is an example which I took from Hunt's text. And this is in section 6.5. So what you see now is that you needed, if you count now, you have 1, 2, 3, 4, 5, and then 6, 7, 8. So you did 8 tests here, or 8, because you don't know what the solution to this equation which we put up here is. So what I put up now is not exactly what we have here. So in general, the way you would set this up is that you would first select a kind of seed number, and that seed number x is one you would start with, and then you try to find the solution to that equation which we have here, this one, because in principle you don't know this number. So you start with a guess, and then you would proceed then till this r, which is assumed to be smaller than the total number n, and then proceed till you actually are able to solve this solution, to find a solution to that problem. As I said, the trivial case is when x is equal to -1 or +1. Then, so you pick a random number that does not have a non-trivial factor in common with n, and then you say that A, or this number which you pick, let's call that the number A, and N, they are so-called co-primes. And this is something you can test with this algorithm, which we call the largest or the greatest common divisor, which you would typically set up. So if that is 1, then the two numbers do not have a common factor and a co-prime. If this number which you pick randomly does divide with N, then you got lucky, and then you have a factor already. So what you would do then to find this order, you would simply then try to solve this equation. And what you want then is to go on till you have a solution to that problem. And when you have found that solution, you have also defined the length of this, what defines this order, which is this R here. Yeah. So this is an R, right? Yeah, so this defines what's called the order of the equations. And when you have found that number, that is when you can go back and figure out what either this one is or that one is. Yeah, yeah. No, you actually is picking a random value for X in the beginning. So that's, and then you're trying to, so this X here is actually is a positive integer, and you want to find, no, sorry, you have a, sorry, I just said this wrongly. You're picking another number than this one, than the X here, and then you're trying to find the one which solves this equation. And when you solve this equation, then this X would be equal to that number which you picked up.
Yeah, so to fix two numbers, the X and R.
Yeah, yeah. So when you, the thing is that this is normally seen, so picking this number randomly, because you would start with a guess. You don't know what this number is. So when you start with a guess, it means that this can easily, if you have a large number, this can easily take a long, long time, and it becomes in principle intractable. That's the basic message when you look at the encryption here to find this final number X here, which are the positive integers X and N, which you, with no common factors, which you, so you want to find X, and then somebody has given you the other part, Q, and then you want to use that to find the final number N. This is something which is essentially a very, very time-consuming algorithm. So the quantum algorithm, or the quantum variant, which is Shor's algorithm, is one which allows us to actually set up these calculations at a much quicker pace and with much less